Inside a modern diagnostic center, a radiologist reviews a high-resolution, three-dimensional MRI scan of a patient's brain. To manage the sheer volume of these scans, hospitals rely on Picture Archiving and Communication Systems, or PACS. This specialized network infrastructure manages petabytes of medical imaging data. The radiologist identifies a specific tissue anomaly in the frontal lobe and queries the system for similar historical cases. While the interface displays results in seconds, the request triggers a complex series of operations within the underlying database architecture. A standard Relational Database Management System, or RDBMS, is optimized for one-dimensional alphanumeric strings. It organizes highly structured data into predictable rows and columns. A 3D MRI scan is a massive, unstructured binary multimedia object. These files lack the clear markers and consistent lengths that relational databases require for efficient processing. To resolve this architectural mismatch, engineers deploy multimedia database management systems designed to index unstructured data. Relational database structures create a technical gap between the storage of these images and the ability to search their contents. Bridging that gap requires a redesign of both the physical storage and the query logic. Before a database can analyze an image, it must solve the physical bottleneck of holding massive files without compromising system stability. Legacy systems forced raw binary streams directly into SQL table cells as binary large objects, or blobs. Storing gigabyte files in relational tables causes severe delays in database backups. It also compromises memory caching, pulling massive payloads into RAM and crowding out critical data. Medical infrastructure needs an architecture capable of supporting massive binary weight while maintaining relational lookup speed. Treating a high-resolution MRI as a simple table entry degrades the entire database's performance. General web development often uses external file references, storing a URL pointer in the database while the file lives on a separate content delivery network. For a standard website, this is efficient, but for diagnostic systems moving gigabytes of uncompressed data, separating files from the database introduces unacceptable network latency. It also creates security risks. When database access controls are physically separated from the file storage, the binary payload becomes harder to secure. This approach also risks orphan files, where a database record is deleted while the external file remains, or a file moves, breaking the database's reference. High-stakes healthcare systems require a database engine that manages both the file metadata and the physical binary payload within a secure, unified boundary. Modern new SQL document databases, like MongoDB, use specific engineering methods to meet this unified storage requirement. MongoDB's architecture enforces a strict 16-megabyte size limit on individual BSON documents. Since an uncompressed MRI scan can easily exceed 50 megabytes, it violates this limit immediately. MongoDB bypasses this constraint using GridFS. The 50-megabyte file is systematically fractured into manageable 255 kilobyte chunks. The system organizes these across two collections. fs.files handles only metadata, while fs.chunks stores the sequential binary payloads, linking each block back via a unique ID. This dual collection architecture allows the database to stream massive media files sequentially without loading the entire object into memory. GridFS bypasses file size constraints by mapping a monolithic binary object to a distributed collection of manageable data chunks. Once the file is stored and streamable, the database faces a second hurdle: how to search the content of the image. True multimedia databases utilize a three-tier model: raw media data, descriptive text metadata, and structural features. Descriptive text is limited. Searching date created cannot identify a specific density anomaly within a scan. Searching the image itself requires the third tier, content-based image retrieval, or CBIR. CBIR deconstructs the image matrix into mathematical models. It extracts multidimensional feature profiles like color histograms, texture maps, and shape vectors. When searching, the database runs a mathematical similarity check, comparing the anomaly's numerical histogram against millions of historical records. By indexing these numerical vectors, the system can perform instant retrievals across petabytes of imaging data. CBIR translates unstructured pixels into mathematically indexable vectors, enabling the database to compare visual content directly. The complex background process concludes in seconds as the diagnostic interface instantly displays matching historical MRI scans side by side for vital clinical comparison. The process relies on two core pillars: GridFS to distribute the physical weight of the files, and CBIR to map the visual logic. This powerful dual architecture allows front-end diagnostic tools to operate with minimal latency, entirely masking the massive back-end computational load. Standard relational databases manage records through alphanumeric keys. Multimedia architectures use mathematical feature extraction to create a searchable index of the visual content itself. By engineering databases to process both the scale and the substance of binary payloads, architects enable medical professionals to leverage global historical data in real time.